Well, thank you for that introduction. And today I want to take a little bit of a more casual tour through a chips to systems architecture of one of the recent cohorts of AI startups in this space. I was chief architect at Groq and did some interesting work there on system architecture, not only from chips all the way to systems. So I thought this would be a nice talk to kind of motivate kind of the system level approach. After all, deep learning is really about building systems. As you know, GPUs have a lot of memory attached to them, but even a GPU with a lot of memory not large enough to run like these large language models, which require multiple GPUs in order to do inference and most certainly to do training. So this will hopefully motivate some of that from a architectural perspective and hopefully motivate what we call kind of the software designed approach or software defined approach, software defined hardware in particular. So a little bit about this talk. We're just going to give some background, talk a little bit about the software defined approach, and then give kind of a hardware software introduction and talk about kind of the system from chips all the way up to multi-chip systems. So first of all, let's talk a little bit about what it means to give reference to the software defined approach. In particular, what that meant for Groq was defining the hardware so that it could be completely controlled, explicitly controlled by the compiler. And this is often different than the approach you normally take. For example, when you build an ISA, you build it with the intent of providing abstraction from the hardware. In other words, you want to provide some agnosticism toward whatever hardware it's running on and provide an abstraction to the programmer or the compiler writer in this case, so that they can reason about program correctness in a reasonable way. And instead, the software-defined approach is about conveying and expressing the hardware at a very low level so that the compiler can build the compiler writer can reason about it and build an effective compiler for it. And this takes advantage of a number of layers of the hardware-software interface, in particular, the static dynamic interface, what you would think about as kind of what done at compile time versus runtime or execution time. And then the hardware software interface, which is typically the ISA, the instruction set architecture. That is, what architectural state is visible to the compiler and how do they comprehend and take advantage of that architecturally visible state. You combine that with the concept of kind of data flow architectures. And data flow is really about building a computation graph where nodes represent the operations and edges represent the data that's flowing between those operations. And there's a very simple concept in data flow, and that is that you build a data flow graph and the operators do not fire until their operands are available and ready. Okay, so it gives you a natural way of expressing instruction level and task level parallelism. And machine learning models are really good fit for this kind of execution model and the abstraction. So we set out to design the hardware to take advantage of this, and really it had to be a pervasive design philosophy to build the chip around it and build the memory model around it so that you didn't have any reactive components. By reactive, I mean things like arbiters and crossbars, things that interfere with the determinism, i.e. being able to know and predict exactly where everything will be at a moment in time. And that includes things like caches and replay mechanisms, things that are often there to accelerate, to take advantage of spatial and temporal locality like caches, as well as reliability, mechanisms that are in place to take advantage of reliability. So the software must have complete access to this architecturally visible state. And then we want to be able to exploit that. And we exploit that through a central concept called the streaming register files. And we'll talk a little bit about that, but that's at the cornerstone of the chip architecture. And this is really all about being able to pop up and deal with complexity. The complexity that arises from building chips often comes from speculative execution, being aggressive in your instruction level parallelism, to be able to exploit parallelism at all levels, thread level parallelism with multi-way, multi-issue, multi-threaded architectures. and instead simplifying that and focusing more on getting more transistors or ALUs per square area. In other words, we want to put more of the silicon to work and take advantage of concurrency. And the main mechanism that we're going to use for that is SIMD execution. SIMD execution is not uncommon, right? It's the heart of every vector processor, every Cray computer out there for the last several decades have really taken advantage of SIMD execution. The other aspect that we want to do is, like I said, avoid complexity that arises at the system level. And at the system level, where you get complexity is in the network. You get complexity from a variety of heterogeneous components. You've got a CPU, and you've got a network interface, and you've got a GPU, for example, and those things are all asynchronous with respect to each other, and they require synchronization and coordination. And that's often done through either shared memory semantics, i.e. a mutex to provide a shared memory variable on which to lock and unlock a semaphore that's used to coordinate and synchronize otherwise asynchronous events. So all of this gives rise to being able to do software-defined networking and software-defined hardware in general. And that is, we know the traffic pattern. The traffic pattern is an emergent property of how we decompose our model, and we shard it. We shard it into smaller tasks that are provisioned onto each processing element, each GroqChip or each GPU or CPU. These get proportioned with some amount of work. And we have to control how that work is executed in the data flows among those processing elements. And that's really at the heart of what we're trying to do. And there's often a lot of techniques that get used to be able to kind of mitigate what for a large part is variation in performance. That variation in performance comes from latency variation, i.e. packet latency, the long stragglers. When you're trying to synchronize across a large number of tasks, you're always going to be limited by the slowest arrival, right? The slowest job. Anyone can relate to this. If you've gone out to a restaurant with 10 of your closest friends, and that one friend that always gets to the restaurant late, you always wait for them before you can get seated, right? That's kind of the long tail events, right? And you want to minimize that and get your variance down so that everyone arrives at the barrier, everyone arrives at the restaurant at the same time, and you can all synchronize from there. So how do we take advantage of this in the microarchitecture? Well, let's take a look at very kind of a canonical tiled architecture where you've got kind of a 2D mesh of tiles, and you've got a very typical 5-stage pipeline, the Patterson and Hennessy 5-stage pipeline. And you can think about the execution units, the functional units in each tile as being doing integer and floating point operations. There's some instruction dispatch and control in each tile. There's also a load store unit that controls the D cache, the data cache, as well as the instruction caches. And then, of course, there's a network component that talks to other tiles and external between chips. What we did is we took this and we disaggregated it into separate functional units, each of which that have their own separate instruction control unit. And what that does is it allows us to treat memory, to kind of remove memory and decouple memory and its storage from the execution units. So now you've got this decoupled execution and execute model where you can fetch the operands from memory and stream them through this online data structure called the streaming register files that flow across and between these functional units. And that's a main idea behind the microarchitecture is you're breaking it into its disaggregated functional units and thinking about those as separate. You can almost think of them as separate, very specific threads that just do one function. For example, the vector execution module just does vector processing. So it does additions and multiplies and ReLUs and hyperbolic tangents and so forth. And it does those on a pointwise basis. And then you've got the big functional units at the very edges of the compute modules called the matrix units. And those are doing deep learning matrix operations, for example, fused dot products and convolutions, for example. And like I said, the thing that connects all these, the conduit through which they communicate, is this concept of stream registers. And stream registers are really what make this unique. And so let's take a pop up and look at this from the 10,000-foot view and take a look at the chip, the functional units and how they're laid out on the chip. This is, after all, a spatial architecture. And by that, I mean the functional units are laid out in a spatial way so that we can take advantage of their proximity with respect to each other. In other words, we're going to lay these out in a way that allows us to flow data across them and capture data flow locality. We're going to, for example, we might do some vector operation and add some bias and then put the data back into a stream where will their flow to a downstream unit and get operated on. And that allows us to take advantage of really nice locality properties and acts as if it's a big single layer cache. The on-chip memory here, as you can see in the middle of the chip, this is called the MEM functional units, and there's 220 megabytes of on-chip memory that store your weights and parameters and as well as your instruction code. In the center of the chip, right at the bisection of the chip, is our vector unit, where we can do 320 element point-wise operations. And as I said, at the very edge of the chip are these big heavyweight workhorses, these MXM units that are 320 by 320 elements. Each element is a byte. So that's 102,000 bytes in each MXM data array. Or we think of these as a plane, a byte-wise plane with 102,000 weights in each. And we're going to use this to be able to give us really good, efficient compute density. In particular, we get over a teraopt per second per square millimeter of silicon. And then around the edge of the chip, you can see here it's ringed with what's called SerDes, serializer, deserializer. And these SerDes are what make up our chip-to-chip or C2C network. And that's our off-chip network. So let's think about how we think about and reason about deep learning compute codes or computational graphs that they represent. Those compute graphs are mapped onto these different functional units. As I said, they have different threads. You can think of these as straight line threads, each of which are very simple in how they're executed, but you can compose them by using these stream registers to pass data between them in a very, very efficient way. In particular, the instruction control unit, the ICUs, there's 144 independent instruction control units. In other words, you can think about this as having 144-way instruction level parallelism. And we're going to take a thread level parallelism, actually. Thread level, you can think of those as independent kind of threads. And that ICU, that instruction control unit, takes up less than 3% of the overall chip area. And that's really quite amazing. That allows us to use the bulk of the silicon for ALU operations. And that's what gives very good density of deep learning ops. So let's again take a pop up again from that and look at the basic building blocks. As I said, the SIMD execution model is kind of the way we think about these functional units, and we think about them as 320 element vectors. Now, in practice, that's actually built from this concept of a superlane, which is 16 elements each, and then there's 20 of those superlanes stacked on top of each other. 20 times 16 gives you a 320 element vector, and that vector is our unit of abstraction. You can think about it like that. We're going to dispatch instruction to a functional unit, and there's different types of functional units. Again, think about this like object-oriented programming. There's different types of functional units, and we're going to take those and we're going to use multiple instances of each type so that we can stream data between them using this data flow concept. And these stream registers, these streaming registers that are literally flowing between the functional units. So how this differs, and I want to just talk a little bit about that streaming concept, how this differs from a normal CPU, for example. You can do a load into a register, for example. You're going to read something from memory and put it into a register, say register 3. And you're gonna operate on that register in a load store architecture. You're gonna do ALU operations on it, and then you're gonna store some result back out into memory, and somebody else can pick it up and do something from there. What this allows us to do, though, is we are going to load something into those registers, and then the register is literally moving, flowing. So the next cycle you have to be thinking about where that data is being consumed. For example, you're going to load something from a memory unit, and it's going to flow to a vector unit where you might add some bias to it. You might add some, do some operation, and then put it back into the register where it flows to matrix unit, and it does some bigger convolution, for example. And you're able to take advantage of that data flow locality. And the compiler is aware of these data locations to an extreme degree. Like the compiler has a Oracle view of the hardware, and it knows exactly where each tensor is stored, where the tensor is flowing, how it's where it's being operated on. So the compiler computes the data dependence graph and then schedules these underlying hardware elements. And again, the key idea here is that we've got lots and lots of memory concurrency, so we can keep all these functional units busy. And this gives you a nice example of kind of how that memory is organized. It's organized as 88 independent memory banks. In other words, there's 88-way memory concurrency. And in principle, each memory can do a read and a write. So there's a total of 176-way memory concurrency. And that's really, really powerful if you want to have a lot of outstanding memory, be able to keep all these functional units busy. Okay. Now, at the heart of this is an ISA that really empowers software so that they can schedule this. And you think about it as using dead reckoning. If you've ever gone kind of hiking in the woods where all you have is a compass, you kind of know you're going to take 10 steps to the north, and then you're going to turn to the east and take another 10 steps, and that's going to get you to a location. So the compiler does very similar kind of reasoning and says, I'm going to use this concept of kind of dead reckoning on a cycle by cycle basis. I know where the data is coming from. I know exactly how long it's going to take to arrive at my destination, and then I'm going to operate on it. And the result is going to be put back in the memory where it can be used by another functional unit, for example. And you can think about this as a really massive, very, very wide VLIW kind of architecture. But unlike a VLIW, all in 144 instruction queues are independent. So it's like they can slip, and they have it's like a differential. You can slip with respect to each other. So the functional units are independent, and you can schedule them together as if it was a giant long word, or they can be treated entirely independently. And that allows a lot of flexibility for software to reason about how data is flowing on the chip. And it's really a very simple functional model that you can think about. You've got these functional units, you consume data operands from these streams, and you put data operands onto the streams. And the streams flow in an east-west direction onto the chip. And that's how you operate on it. And that's really the kind of functional model that the compiler has for taking the computation graph, decomposing it, building a dependence graph, and then mapping it to these functional units. And as I said, the heart of this is a domain-specific ISA. And by domain-specific, I mean it's designed for deep learning. So there's specifically just those operations that you need for deep learning. We don't run an operating system on the chip. The operating system is run by the host CPU. And this is really considered just a domain-specific accelerator that's accelerating a big chunk of the compute graph, which is a big part of the actual execution time. But we're not going to concern ourselves with booting Linux and running all the general purpose computing tasks that go on in a CPU. So in particular, each functional unit has a number of instructions that are just specific to that instruction unit. So for example, the memory unit does reads, writes, gathers, and scatters, and it has some ability to do iteration. So you can set up these essentially concurrent loops and have it iterate through the loops, generating the addresses that you need. So it takes care of address computation. And then the vector unit has all the unary operations, binary operations for pointwise operations, including things like exponentiation, transcendentals like hyperbolic tangent, and reciprocal square root, for example. The matrix multiply unit, the MXM, has all the weights, and we use those weights like in a systolic way. We load the weights, and then we run activations across it, producing a fused dot product, and we can accumulate those results over time. And then for data manipulation, we've got what we call the switch execution module. And this is the on-chip switch or the on-chip data movement, which allows us to take these vectors and shift them up on the chip. So literally shift the elements up or down to be able to permute those elements in an arbitrary way, or to do transpose operations, for example, where you're switching the rows and columns of a tensor, to do that very, very efficiently. And then lastly, we've got this chip to chip where we communicate across outside the chip, so to other chips in the system, and that's all managed through this concept of chip to chip module. The data types that are supported are common to deep learning models. We don't support things like FP64. We support up to FP32 in the vector units, and the large deep learning operations that are done in the MXM operate on both floating point FP16 and signed and unsigned integers. And what the matrix unit is doing, you can think about it as producing a large 320 element fused dot product. And what that does is it allows us to keep as much accuracy as we can, since we're not, repeatedly rounding off those values. We're doing this, huge 320 element fused dot product, so we can preserve as much accuracy as possible. Now, lastly, all the functional units have some things in common, because after all, central to this idea is you have to be able to fetch and execute instructions. So naturally, every instruction unit has the capacity, the ability to fetch instructions, to execute no-ops, which essentially models the passage of time. So if you want to wait for your data to arrive, you simply do a no-op for some number of cycles. And that's the central mechanism for coordination of data elements as they flow on the chip. But however, if you cannot keep a synchronous model, if you need to synchronize, as you will when you come out of reset, the functional units are all loosey-goosey and they're operating completely independent of each other. And first thing you need to do is park them and do a synchronization event. And to do that, we have two instructions. We have a sync and a notify, and that notify wakes them all up in a staggered manner so that they all have the same sense of global time. So when the chip comes out of reset, you do an initial sync, you notify everything, they all come up and start executing in lockstep. And that's critical, right? We get them all executing in lockstep, and then we keep it that way. We keep it that way for the duration of the program. If you ever needed to resynchronize, you have the mechanism to do that with that sync and notify. As I said before, the MXM is really a big component to where you get a lot of your compute power from, and that's really these 320 by 320 operations. And we use those to do large matrix operations. Like I said, you take your problem, you break it down into 320 element vectors, and then you're going to operate by doing some n by 320 by 320 by 320 operation. So for example, you break that down and you do multiple operations, and then that can either be int 8 or floating point FP16, and that's on these MXM units, like I said, which are at the edges of the chip. So you got data that's flowing on the chip kind of in this east-west way, and you're loading data into the MXMs, and you're producing results which then flow back in the opposite direction. At the center of the chip, as I mentioned, is the vector processing units. And those vector processing units are really, really fungible, very flexible processing cores that that do all the other, everything that's not a big matrix operation. So it's doing all the pointwise elements. It's doing your ReLU, your activation functions, and you can take those 16, each vector unit has 16 ALUs, and they can be chained together through a process called vector chaining. And we use the stream registers to capture that locality. So for example, in this example, I'm going to do some ALU operation, and then I'm going to flow the result to this other ALU to do some other operation B, whose output will go to C, and then therefore go to D, and then kind of out the other way and back. So you see, you can kind of very explicitly control how data flows between the different ALUs and coordinate that. So you can get a very typical kind of accumulation, add, do some activation, cast that result into a floating point, and then do something else. again, at the heart of all this is we have to have gobs and gobs of memory bandwidth. So we take advantage of about 55 terabytes per second of on-chip SRAM bandwidth. So that's a lot of on-chip bandwidth. And we couple that to our streams, which are carrying, the streams can carry up to 80 terabytes per second. So the stream capacity obviously has to exceed that of the memory capacity because it's carrying all the memory bandwidth. So the memory bandwidth is like I said, 50 terabytes per second of SRAM bandwidth to be able to read and write to and from memory and keep all these functional units fed. And then a kind of the Swiss Army knife on the chip is called the switch execution module, which is a bit of a mouthful. But the SXM contains all the functional units for doing permutations, transpose operations. Kind of think about it as on-chip data manipulation, where very common in machine learning codes. To have to just move elements around. For example, if you wanted to take advantage of sparsity, you can use the SXM to very quickly prune out inactive or zero elements in the vector. And it also has what we call the chip-to-chip module. It's also where the send and receive units are for our chip-to-chip components. Okay, so it's all the on-chip communication and off-chip communication. Now, so we've got a bit of a background here on the chip itself. How do we tie these together to actually make usable systems? After all, when we designed this, 220 megabytes we thought was going to be adequate to handle the capacity of many machine learning and convolutional networks. At the time, large language models weren't a glimmer in someone's eye, right? I mean, it was really very early, and we were focused more on convolutional networks for image and object detection. And so each element has roughly 220 megabytes. And then what you want to do is take larger models, and those get decomposed, and you scatter those, and you take the model and you spread it across many chips to take advantage of concurrency. And so what that does is it produces kind of a natural boundary of packaging hierarchy and a system hierarchy. And that corresponds to a single chip being packaged onto a card. And that card has a number of cables coming out of it. We'll see that in a moment. And multiple cards. Cards get stuffed into a node. And then we stuff 9 nodes into a rack. And then we stuff many racks into the cloud, right? So you can see this kind of turtles all the way down kind of hierarchy. But that's really what we're building upon. We're building upon abstractions and the hierarchy within that. So when we think about kind of what we're trying to do from a scale out system organization perspective, we're trying to build a network of processing elements, a network of Groq chips that has both low diameter, and we can schedule it entirely in software and take advantage of hierarchical packaging. In other words, where we have cards that are packaged together closely, we want to use electrical signaling that's abundant and cheap and connect those as richly as we can, take advantage of communication locality and packaging locality. Things close together can often be connected for relatively cheap. Nodes that are further away in different racks, for example, will be connected using fiber optics or optical links. And then lastly, what we're going to talk about here is our chip-to-chip links, how we flow control those, how it's dramatically different than your typical InfiniBand or Ethernet that kind of are part of the data center network. This is really about building a high-performance, domain-specific network that can take advantage of the underlying power of the chip. And so what we've done is we built out a scale-out organization that captures these principles, and in particular, it builds a Dragonfly topology. And Dragonfly is a hierarchical direct network. So each chip is providing both processing elements and the communication switching components that it needs for communication. A single chip is doing both the processing as well as the switching elements of that. That allows us to keep, number one, it allows us to keep the number of components in the system relatively low. The component count in a large, multi-thousand chip system has to be kept as low as possible because your reliability of the system will be directly related to the number of components that you have in the system. So if you have, a GPU and a NIC and a CPU and a switch chip and then a PCIe bridge chip and a bunch of additional components, all of those kind of erode your reliability, your fit rate. It's called your failures in time, or your fit rate of the system, and that erodes it. So we wanted to build this scalable Dragonfly topology to be able to exploit that packaging locality. Like I said, within each node, the TSPs, the Groq chips within each node are richly connected using this wiring mat here. You can see there's 28 cables stuffed in this little 4U chassis. So it's a kind of a neat trick to be able to take all these cables and very densely fold it into this node and tuck that all under in a nice way that it allows us to take advantage of low-cost electrical signaling within the node, and then between the nodes or among the racks to use fiber optics where necessary. Excuse me. All right. The additional thing that Dragonfly allows us to do is to take advantage of a very regular and symmetric, both edge symmetric and node symmetric topology that allows us to build in a spare node. As I said, this is a deterministic architecture, and so we have to have a viable way of dealing with dynamic failures. And when a node fails, the runtime detects the runtime. When you go to launch an application, you have to, number one, marshal the resources that you're going to need, find the processing elements you're going to need, put them together and make sure they're all healthy and communicative. And then you can start distributing your collateral, your code that's going to run on each, as well as the weights that they're going to be executing. Right? And so if one of those nodes are down, you don't want the whole thing to come to a screeching halt. You want to basically, metaphorically, move it out of the system and move it out of the way, find a workable set of nodes, and then shard your model onto those available system while you fix the downed node, while you fix it, replace a power supply or whatever needs to be fixed. And then you can bring it back in. So there is an element of being able to react to some failures, but that reactivity is really handled by the runtime. So when you go to invoke the program, it makes sure that you have a viable set of known good elements on which to operate. And what the Dragonfly topology does in particular is it builds a scalable group, a local group that are tightly connected. And these 8 processors, these 8 TSPs, each have 4 external ports that allows us to interconnect a 32 port group. So that 32 port group acts like a virtual router. And we can use that like a 32 ported router, like you would use a router. And they're all very tightly interconnected. So we have all those cables within the node allow us to very tightly connect this set of TSPs. And in fact, we provide a 2x speed up. In other words, you have twice the bandwidth inside that local group than you do outside of that group. And that is a requirement, a canonical requirement for the Dragonfly topology, because you're going to use that speed up to do adaptive routing. And in particular, in this case, we're not going to dynamically route packets. In other words, we're not going to actually be sensing congestion dynamically, but rather we're going to obliviously spread that traffic out, take a non-minimal hop. In other words, if I wanted to go from this TSP to TSP3, I can go directly where I have a direct connection, but I can also go indirectly by taking a hop to this one and then to this one. And so there's what that's called non-minimal routing. And by taking that additional hop, I'm using up some of my internal bandwidth, but I'm getting a lot of additional bisection bandwidth by being able to just be able to soak up and use up all the available bisection bandwidth across the node and between the nodes. And so this allows us to build systems that are up to several hundred Groq chips, and all the way up to several thousand with a more scalable approach here as we build this out even further. So how do we actually keep these things synchronized? What does global synchronization look like in a system that's built using plesiosynchronous links? So the links that are connecting all the different TSP chips are plesiosynchronous, which is just a $5 term that means they're mostly synchronous. And they're synchronous with respect to the tolerance of the crystal chips that are driving them. Okay, so you can think of this as they're almost synchronous. They're kind of close, but not quite, right? They have tolerances on the crystals that are driving them, and that tolerance is about 50 parts per million for a good clock crystal. And that variance, that skew, if you will, that drift that accumulates over time is essentially compensated for using software and hardware techniques. In particular, we use a combination of software and hardware counters to detect the drift, and then software counters to compensate for it, to kind of factor out the drift that you would observe between the different compute elements. And this allows us to keep, even though all these chips are actually running independently, we can provide the illusion of a globally synchronous system that is running across thousands of TSP chips. And that is really kind of the secret sauce to being able to scale this up from, simple convolutional neural networks that fit on a single chip all the way to large language models. And I see Groq has the newest Facebook Llamas large language model running on their systems now as well. So they're able to take that up and scale it all the way up, so you can do many, large multi-gigabyte, kind of all the way up to terabyte scale kind of models, and spread that across the chips. Not only do you need to spread it for memory capacity, but you also need the compute capacity. So you really do need to shard and spread these models. Even if you had magically you had enough memory to fit the entire model in memory, you need to dispatch it across multiple workers just to be able to distribute the computational load. So in order to do this, like I said, we've got a number of ISA support. In particular, we maintain this notion of hardware and software alignment counters, and then we have specific instructions that we call the deskew instruction, that allows us to basically compensate and to factor out that additional drift that we detect. And that's maintained in a very simple way that allows us to maintain this determinism, because when you start the system, you're going to be aligned and they're all independent, and then they may drift. Like I said, they may have a slight difference in the notion of what is kind of global time, right? And we're able to kind of compensate for that at the system level. And that's what allows us to do the software scheduled network. In other words, we can treat the network just like we treat any other functional unit. We schedule tensors on the network, just like we would schedule them on an ALU. It's just going to go from at certain time, we're going to start sending a tensor across the wire, and we know exactly when it's going to arrive on the receiving side. In order for us to do that, however, we needed to kind of understand all the sources of non-determinism, because a normal network will have, for example, a replay mechanism. They'll have a reliable communication replay mechanism. For example, PCIe has a sliding window go back end protocol. So they send packets, and if a packet gets corrupted at the receiver, it just gets dropped. The sender times out, he resends it, and it does that until you get a good packet sequence. And that obviously doesn't work well for a deterministic architecture, because it would obviously perturb the time relationship between when things are sent and received and expected. So instead, we have to do forward error correction. That is, we send the data. If there's a fault or a corruption in that packet, we run it through a forward error correction Reed-Solomon detection scheme, which allows us to correct simple errors and detect multi-bit kind of burst errors. The other thing that we do is there's no adaptive or dynamic routing. Like I said, we don't want to do congestion sensing. Those are reactive components. That makes it a reactive system. And instead of sensing it, we want to spread and schedule the network links so that we can load balance them deterministically. Adaptive routing is all about load balancing. Instead of doing that reactively, we do that from first principles. And we take the tensors and we're going to be able to spread them and schedule them. And that way we can avoid congestion instead of having to sense and react to congestion. And then the idea here is that we're going to be routing tensors, not packets. So there's no encoding overhead. We don't even encode what a packet looks like. We're sending tensors. And so when you start sending something, you're going to be getting a sequence of vectors over time, and that represents a tensor. And so you can think about building up, and instead of sending messages, you're sending tensors. And so the fundamental data that you're sending, it looks different, right? Instead of sending messages that are based out of packets, you're sending tensors that are built from vectors. And so this is what I mean by a domain-specific network. It's really designed to operate on the fundamental data types that are flowing in the system that are specific to deep learning. And this really gives an example of what I meant when I said you're taking your network, and there's always one minimal route between every source destination pair, but there's many non-minimal routes. And we can take advantage of that by doing non-minimal routing. And that's really how we take advantage of, instead of doing adaptive routing, we're doing non-minimal routing to spread the traffic across as many links and schedule it across as many links as we can. And that reduces the amount of serialization time it takes to send a big tensor. For example, if you're sending a big, 6 megabyte tensor across a bunch of narrow little channels, you want to spread that out so that you can reduce the serialization latency across the network. And as I said, the beautiful thing about the Dragonfly network here is it is both edge and node symmetric. And so you can take advantage of, it simplifies your scheduling, how you view the network. Everything looks the same. For example, I'll give it to contrast that with a mesh network, for example. In a mesh, the nodes that are sitting at the edge of the mesh do not look the same as the nodes that are sitting internal to the mesh. They have different channel loads. They have different number of ports they can use, and that is not symmetric. And it makes the finding a set of resources and then scheduling those resources much more difficult. So instead of adaptively in sensing and adapting or reacting to that congestion, we're spreading and load balancing and scheduling the adaptive routing, or the packets on the vectors and tensors on the network. You can see there's very direct analogs between messages and tensors and packets and vectors in this case. So as an example of which we think about the network as very, very simply, instead of a typical RDMA type use case where you're going out and reading somebody's memory and he's sending back querying the DRAM, he's getting the reply, and that NIC sends the reply back, and then later we can use it. That's a multi-step kind of way to do an RDMA. Instead of that, the compiler knows ahead of time when the data has to arrive, and can basically pull the data out of the memory and sends the vectors across the network. And so it arrives just when it's needed. And in this way, you literally avoid the request reply transaction, just becomes the reply. The request is handled almost implicitly by the compiler, right? The compiler kind of knows when that request is arriving, so to speak, and when the reply data is needed. So as I said, reliability and scalability are really two sides of the same coin. In other words, if we want to scale the large processor counts, we have to be able to do so reliably. And in order to do that, we had to design some reliability features into the chip. So one of the things that we did is we designed it to have 21 super lanes on chip. So there's an entirely redundant super lane. And we do that because these chips are very, very complex, and there's manufacturing defects, and we want to be able to operate in the presence of a failed superlane. And we are able to do that. And this is the one area of the chip for which we actually hide the details. And this is remember I said it's not about abstraction of the hardware, it's about controlling the hardware. And this is the one example of where it is about abstracting away. We hide the fact that there's 21 superlanes, one of which can be defective. Doesn't matter which one, we hide it. And this is the one area that the hardware does indeed abstract away some things from the software, because that's completely invisible to software. And that only allows us to be able to, number one, increase the yield and be able to, like I said, survive a bad superlane and provide some redundancy. So every TSP chip has some redundancy. And then we actually have, like I said, determinism that simplifies the design and verification of the chip. And this is really about how we build chips. And that is, building a deterministic chip in many ways is simpler than a chip that has a lot of complexity and a lot of non-determinism, a lot of cache controllers, arbiters, crossbars, things that permute the ordering of events in a way that makes it difficult to predict. And so we're able to express these relationships between the functional units. Like I said, there's a spatial architecture. They're laid out next to each other. And in a very producer-consumer kind of way, we can express those relationships in a assumption and guarantees formalism that allows us to express assumptions among producers and guarantees of consumers, and then flip those around and make sure that they are in fact being satisfied, so that we have a good hardware underneath all of this. And then, like I said, exception handling is difficult when you're building a deterministic system. Exception handling is difficult, and that's just part and parcel of building scalable systems. And what we do is try to resolve as many exceptions ahead of time. How do we do that? Well, one way that we do that is providing instructions that give saturating and unsaturating behavior. In other words, you don't have to worry about overflowing your ALUs and causing an arithmetic exception, because there's separate instructions that say you decide the semantics of how you want those to be handled ahead of time. So you want to do a saturating add operation, you know that the behavior of that add, even in the corner cases. And so we try to resolve as many of those exceptions up front. And then, like I said, we provide forward error correction and SecDed, single error correction, double error detection, on all SRAM and all hardware structures, including the stream registers. So there's literally end-to-end kind of SecDed, end-to-end ECC on the chip. And that's critical. You want to be able to kind of tolerate as many errors as you can and just kind of keep running. And that allows us to kind of put together this robust software stack that allows software to kind of think about things without having to deal with too many of this exception handling, because that's what throws a big wrench in a software stack where you're trying to handle that determinism. And so this ECC Everywhere, like I said, is really fundamental to the chip. We put error correcting codes on all the stream registers so that we can correct any single bit error that may arise in the system, and they will happen, right? They're going to happen as just a matter of getting a gamma particle from outer space come and hit your SRAM at just the wrong time, and it's going to flip a bit. And we're going to be able to, identify that flip bit, correct it in situ, where it'll like it never happened. And we put that on all the instruction control units, as well as the SRAM units, as well as the streaming register files. So we had to pay some overhead, but it's well worth the cost. And that cost is relatively small, since the ECC is amortized for, like I said, these 16 elements in each streaming register, carries 16 elements. And we're able to amortize that ECC cost across that. And like I said, it really pays to be paranoid. Our sun is a big source of high energy helium, high energy gamma particles, and those come to Earth and make it through our magnetosphere and troposphere and ionosphere and land in your data center when you're least expecting it. And unfortunately, this is there's some flux to the cycle. It varies. And you can see here that it's an 11-year cycle, and it's going to be at a maximum here in the 2024 timeframe, just when a lot of these systems are being deployed for large-scale machine learning. And so we have to be very careful when we design our systems to take account for all these things that really matter. And this just shows you how we protect all those critical hardware structures. This gives a detailed breakdown of the hardware pipelines and really shows all the stream registers on the chip. And you can see at the very edge, at the very left edge of the chip, we've got our matrix multiply units. And then each of these gray boxes is a stream register. And you can see every one of these gray boxes is actually how the data is going to be flowing between those different functional units. Okay, like I said, NANDs and INFs, arise in the wild. It's a thing that happens. You have to be able to have the hardware to be able to detect it, handle those arithmetic exceptions, avoid those arithmetic exceptions, and then come up with a simple replay mechanism. And we call this kind of a one-shot replay on an error to see if the error is a transient error, for example. If you're doing an inference, you're doing a forward pass through the model, and you get, if you the output at the output of that model, you go, oh, I got an error. I'm going to replay that inference and try it again to see if that error was a transient error. Often the case is they're transient, right? You may have some signal noise or some weird oddity that a loose connection somewhere that just by replaying it fixes it. Obviously, if that happens repeatedly, then you might have some flaky hardware that you need to reseat or to change about or to accommodate in some way and run a machine doctor on it to actually diagnose. But the idea here is that you want to be able to tolerate any kind of error, keep on running as long as you can, and when you absolutely can't, you want a replay mechanism to be able to replay your inference. So just a couple of simple workload evaluations to show you, the hardware is working and doing what it's supposed to do. And we ran it on a number of kind of HPC and machine learning workloads. And this is actually on a Cholesky decomposition to show kind of the scaling across the single chip all the way up to 8 TSPs in a node, and how the data is actually kind of decomposed. So we're taking this triangular matrix of a symmetric positive difference matrix, and we're breaking that down and chunking those up into rows, distributing those rows on the different chips, and then executing that in parallel. Natural language processing with BERT. We had a paper on this. I'd encourage you to go take a look at it. It was called Answer Fast. It was about optimizing BERT for low latency. And this is just a nice example of the latency variance that we experience. Very, very, very little. You can see the execution time here is just a big spike, right? There's no tails really to it. And that's the variance that we do experience here is actually from the PCIe channel of actually loading the inputs onto the device. There is a small amount of variance that happens because of PCIe, transmission errors happen. And so you can see, for example, the speed up compared to A100s was pretty significant. We get a 6x speed up. And moreover, the variance in the 99th percentile and the 95th percentile and the average is virtually dead, spot on. It's within a microsecond. Whereas if you look at the A100, it's a much wider variance, right? 630 microseconds on average, with variance up to 790 microseconds at the 99th percentile. And then just to look at kind of the workhorse, really heavy lifting is matrix multiplication, and just a GEMM matrix multiply. This is kind of, if you were to sweep through a bunch of different matrix sizes, this is how the TSP performs relative to an NVIDIA A100. And this is really a little bit about kind of hardware fitting. You see how GPUs and CPUs tend to have certain sizes that they're amenable to, and sizes that just don't work well. And you can get anywhere from half utilization all the way up to 80% utilization for something that fits really well, right? And this is a good example of how the TSP as a domain-specific accelerator really, really functions well in that domain, and it's really designed for those workloads, and it doesn't have that kind of sensitivity to the matrix sizes. You know, it doesn't have the kind of sensitivity that a GPU or a CPU would. And lastly, as an example, let's look at a common traffic pattern that is used, and this is the AllReduce. AllReduce is the bread and butter for synchronizing between the different tasks. And we see that even though the Groq network has less pin bandwidth, in other words, the A100 is actually signaling much faster. It's signaling at twice as fast per chip, and there's more ports, but we're able to take advantage of the pin bandwidth that we have much more efficiently and avoid the unnecessary synchronization. And you can see as you look at the tensor size, as we sweep through the different sizes of tensors, we're able to get really good utilization from very small tensor sizes. So you don't have to have, you know, really large messages in order to get good utilization. You can take advantage of the network efficiently at very, very small sizes. So all of this, like I said, was to really motivate how we're building the hardware to take it, or building the hardware so that the compiler can target it and make good use of that. And so the compiler informed our hardware design, and the hardware design matured. And obviously, as the chip finished, we're able to then take it and build the compiler, finish the compiler around it. And here's what the list of, this is a little bit stale now, but you see it as the growth rate, I guess, of being able to target the hardware with different models. And those models vary too. They're not all just convolutional or computer vision models. They're text-to-speech, natural language processing, as well as some high-performance computing models. So really, all of this, like I said, was really targeting how do we build low latency, high throughput systems that are really well designed for these compute-intensive deep learning tasks, and then delivering predictable and repeatable performance. That's the difficult part, dealing with the tails of that distribution. And what I hope I motivated here is that the mechanism that we use really allows us to build reliable, scalable systems that are really great for low latency. I think about low latency, I think about batch one inference, right? When you're trying to deliver a service, you want to be as efficient at batch one inference as possible. And that ISA at the heart of all of this, the instruction set architecture, is not about abstracting away the hardware details. It's about exerting control over the underlying hardware. And we do this through this concept of programmable instruction control units, 144 of them corresponding to different spatially organized functional units. And we expose that architecturally visible state to the compiler where it can take advantage of it. And then lastly, we extend this across multiple chips so that we can take advantage of software schedule networking and build large-scale systems that are much more amenable to tackling these large language models, large models in general, in a way that allows us to treat the entire system as if it's a large synchronous single chip, as if it's a single chip, right? But it's obviously not. It's an abstraction, but the compiler thinks of it as if it's a large single TSP. And what it allows, if you're familiar with this, is it allows for lock-free communication. It allows you to communicate between any two processors in a way that doesn't require explicit coordination, right? Doesn't require you to signal through a mutex variable to the consumer that the data is present, and then the consumer then consumes that data. So it avoids that additional step, which is tremendous in terms of reducing latency and improving the overall efficiency of the system. So thank you. I wanted to thank the audience here, and if there's any additional questions, certainly feel comfortable reaching out to me or anyone at Groq. I think it's a good example of one of the recent domain-specific accelerators, and I hope you found it useful.